Okay, so welcome to the third and last talk of today's session. We have Scott Larson from University of Georgia telling us about positivity in weighted flag varieties. Please take it away, Scott.
Okay, yeah, thank you very much for the invitation and introduction. Yeah, today I'll talk about positivity in the equivariant cohomology of weighted flag varieties and its joint work with Bill Graham. So a flag variety is an orbit of a connected complex reductive algebraic group on its set of parabolic subgroups. There's new stuff in this talk, even for GLN. So you can assume G is GLN if you'd like. Invertible complex n by n matrices. Fix a cartan and an isomorphism with a product of C crosses. So in GLN, take the diagonal, and the coordinates of the diagonal is this isomorphism. Fix a Borel containing the cartan and a dominant character of the cartan. With this isomorphism, you can think about it as a tuple of integers, just keeping track of the exponent in each factor. Extend this character to the Borel by making it trivial on the unipotent radical, and then choose a parabolic containing the Borel small enough such that lambda extends to it. So C lambda is a one-dimensional representation of this parabolic subgroup. There's a corresponding equivariant line bundle on G mod P, the flag variety. And Z is going to be the complement of the zero section of this line bundle. So there's a projection from Z to the flag variety, making it a C cross principal bundle on the flag variety. So for example, if you have GL, say n+1 in mind, with the diagonal, B is the upper triangular invertible matrices, you can choose lambda to be the projection from the diagonal to the first coordinate. Choose P to be the maximal such subgroup. So the levy of the parabolic is just 1 by n diagonal matrix, size 1 block and size n blocks, and then shade in the upper triangular. There's a proper map from this line bundle to the standard representation of GLN +1, where the scalar Z in the C lambda scales a vector, and then G is really acting on the left by column vectors. It's just matrix multiplication if you think about columns. So if you restrict to Z, then the scalar is non-zero, and so matrix multiplication will take a non-zero vector to another non-zero vector, and so you can think about G equivariantly as the non-zero vectors in the standard representation. So that's going to be the running example to keep in mind for this talk. So Z is, as before, the C cross principal bundle on G mod P. Now we're going to choose a co-character under this isomorphism, the fixed isomorphism of the cartan. It's just another tuple of integers. W's can be the Weil group, and the key assumption that's making everything work here is for every Weil group element, assume that the W translate of lambda paired with the co-character is strictly positive. Set S to be the subtorus of H, which is the image of chi. The weighted flag variety is defined to be the quotient of Z by S. So the first fact is that X is a projective variety. Anything you know about the flag variety, you want to pull up into Z and then quotient out by S. And the corresponding topic or object you get is called the weighted thing from the original flag variety. So from the previous example, if you choose chi to be a sequence of positive integers, the W translate of lambda just moves that 1 to whichever coordinate you want, and then the pairing with chi picks out the corresponding integer. And so if you choose positive integers, it satisfies this key assumption. In this case, X, the weighted flag variety, is weighted projective space like you would find in an introductory algebraic geometry book. Okay, so now I want to start with the open affine cover of the flag variety, pull it up into Z and quotient it out. And some of this notation is, maybe if you've seen it before. So if you start with an open affine cover or one of the open affine subsets of G mod P and pull it up into Z, and then quotient it out by S, call that U sub W. So it's possible to prove that this U sub W is a finite group mod affine space, and consequently, the weighted flag variety is an orbifold. I have this open cover by finite group mod affine space. Do the same thing to the Schubert variety. Start with a Schubert variety in G mod P, pull it up into Z, quotient out by S, call that the weighted Schubert variety.
But there is a question from Alan. Is the key assumption satisfiable when G is semi-simple? It seems like okay.
That's a really good point. So yeah, if you look at SL2, W changes lambda to its negative. So yeah, so any semi-simple group will not satisfy this. So central extensions are key to this theory. And in the literature, a lot of times you start with a semi-simple group and extend by a C cross, but you don't need the group to be of that form.
All right, thank you.
Yeah, good question. Set T to be the quotient torus. So this is going to be the torus acting on the weighted flag variety, and it looks a lot like the normal torus acting on the normal flag variety. So the fixed points are indexed by the Val group or WP in the case of G mod P. A lot of things look the same except for the weighted flag varieties and orbifold with singularities and not necessarily a homogeneous space. The fact that the weighted flag variety is rationally smooth allows us to consider Poincare dual classes of weighted Schubert varieties in equivariant cohomology. And a key fact proved by Abe Matsumura is that these classes form a basis of this ring over the equivariant cohomology of a point. So here's our main theorem. Given any two Weyl group elements, on the left-hand side, write the product of the Schubert classes, the weighted Schubert classes using the ring structure. And on the right-hand side of the equation, expand that element in terms of the basis. And so the CUVWs, which we call weighted structure constants, are elements of the T equivariant cohomology of a point, which is really just a polynomial on the Lie algebra of the torus. So these CUVWs you can think of as polynomials. We're going to define script S UVW as the support of U and V lying over W, which is the Weyl group elements, at least W and at most U and V. And for simplicity, we're going to assume chi is anti-dominant, which is not super essential, but it's going to make things a lot easier to state. So for any UVW in the Weyl group, this is our main theorem. The equivariant structure theorem is a non-negative sum of products of negative simple weighted roots at elements of the support. So I'm going to explain this a little bit. First, I want to say the history, a little bit about the history, and then tell you what weighted roots are. Okay, so under this key assumption, it's a fact that there always exists a co-character whose image is contained in the solvable radical of G. And in this case, the weighted flag variety is just the usual unweighted flag variety. And the torus is a maximal torus as usual. And our theorem actually reduces precisely to this famous positivity result proved by Bill Graham back in 2001. If the group is C cross times GLN, and lambda is of this particular form, so the weighted flag varieties in this case will be examples of weighted grassmannians. Abe Matsumura proved a similar theorem, somewhat weaker, but they have a similar positivity statement if you replace the support with just the maximal Weyl group element. So it turns out that using the support is a strengthening of just using W naught. There's another article considering equivariant cohomology by Azam, Nazir, and Qureshi, but they do not consider positivity at all. So that's the history related to this theorem. So what we do is we generalize the definition of weighted flag varieties. So it's slightly more general than you'd find in the literature. We prove the strengthened positivity result, which is using the support. And we interpret all of the parameters geometrically in terms of weighted Schubert varieties and weighted roots. So one of the things Abe Matsumura state in their article is that they don't have a geometric or representation theoretic interpretation of the parameters. So that's one thing that this is doing, even in that case. Okay, so here's weighted roots. You can think about a root in a flag variety, so do the same thing, pull it up in a Z and quotient it out. So roots connect the H fixed points in the flag variety by H stable curves. So if you fix a T fixed point, call it W, then the open affine around that will be a sum of root spaces, call it C alpha. So the C alpha is at W. Pull it up, the C alpha cross CW lambda star is viewed from H. That's what the pre-image in Z looks like in this principal bundle. Quotient out by S, that's going to be a sum weight given by some weight of H, which is what we call the weighted root. So that's where weighted roots come from. Just to say it a little bit more explicitly, given a character of H, set the integer of gamma paired with chi to be A sub gamma, just for a little shorthand. So given a root of H and G, define the weighted root corresponding to alpha at W by alpha of W but to be this quotient. So for example, if the image of chi is contained the solvable radical as before in the unweighted case, the A sub alpha is 0, the A W lambdas cancel and you just get the root again. So all the weighted roots are just roots. It's kind of fun playing around with these things at different W's. So if V is less than or equal to W, then a negative simple root at V is a non-negative linear combination of negative simple roots at W. So if you have a positivity statement at a smaller element, you can replace it with a weaker statement, getting a positivity statement at a larger element, which explains the Abe Matsumura results from ours. Okay, so we have a weighted Chevalley formula, just to see an example of some of these positive structure equivariant structure constants. Weighted structure constants. So if you start with a character of H, write gamma bar of W to be this gamma minus A gamma over A W lambda times W lambda. This is a positive scalar multiple of a weighted root. And it turns out to be easier to work with these. But if you have positivity in the bars, you have positivity in the weighted roots. QW is this rational number that's a quotient of some things coming from stabilizers of the weighted Schubert varieties, but I'm not going to go into all the notation of what QW is. It's just some positive scalar. Let alpha be a simple root with the reflection in the vowel group, not in the vowel group generated by the parabolic, and then let u sub alpha be the corresponding divisor. So this is indexing a codimension 1 Schubert variety in G mod P. Choose omega alpha to be a character of the torus, pairing with the other simple co-roots with Kronecker delta. So there's lots of choices for omega alpha, but just choose one. It doesn't matter what you choose. So here's the Chevalley formula for every vowel group element. We have if you expand the product of the class at U alpha and UV at V, you get this QU alpha times a sum of negative weighted simple roots. So the way to think about this, W naught omega alpha minus V omega alpha, you can write, without the bar, you can write that as a linear combination of negative simple roots. And then the bar is a linear operator, so you get more or less a non-negative linear combination of negative weighted simple roots at V. Okay, so it's at V, and V is in the support of U alpha and V over V.
15 minutes.
Okay. And then maybe I'll skip the other one. It's just some number that turns out to be, well, it'll be the non-weighted structure constant in this case. But I want to show you another example in weighted projective space. So the first equality there is a Borel type presentation that holds in any case in complete generality. That seems to be new. And then in weighted projective space, the second equality holds, which really doesn't hold quite as generally, quite as nicely. In this presentation, we can describe the weighted Schubert varieties as the GCD. Remember, for weighted projective space, you choose positive integers A0 up through AN. And so take the GCD of A0 up through AK and multiply by the remaining variables, and that gives you the class of the Schubert variety. So here I'm indexing where V0 is less than V1 is less than all the way up to Vn. So Vn is the biggest, V0 is the smallest. Okay, so here's my favorite example to think about. If n equals 4, so there's 5 variables. We're working really with P4 or 4-dimensional weighted projective space. Choose V2, expand delta V2 and times delta V2 at V1. Then the support of V2 over V1 is just V1 and V2. And if you ignore some of the positive constants, this table shows you what that weighted structure constant is at different weighted roots. And so now you can see really where you need the support for the positivity statement. If you look at the expansion of the equivariant of the weighted structure constant at V1, you can see there's choices of chi making some of the first term there negative. So if you look at V1, this first number here turns out to be negative for certain choices of chi. But if you look at V2, no matter what chi you choose, that's going to be a positive or a non-negative combination of negative weighted simple roots at V2. Okay. And then Abe Matsumura would work all the way up at V4, and you can still see it's positive there.
18 minutes.
Okay. Let me stop there for questions. There's lots of future work, but maybe I'll take questions instead if there's any.
Well, first of all, let me thank you for a great talk. Thank you, Scott, again.
Yeah, thanks.
And in fact, let me thank all the speakers for today, Francoise and Joy and Scott again, and thank you for your great talks. And thank you everyone for joining us. So this was the last seminar for the year. Please stand for the questions, and then we're waiting for you to see you the next year when we restart sometimes in January or maybe early February. So thanks again to everyone, and we'll take questions.